Had the digital computer been around back in 1924 in any significant kind of manner, it's likely we would never have had an Xbar based upon the range control chart. Instead, we would have had nothing but Xbar control charts based upon the sample standard deviation. Now, oddly enough, it's going to turn out that it really doesn't matter which one we use because of a couple of factors, but we'll summarize that or we'll get to that when after we develop one of these Xbar charts that are based upon the standard deviation. Ultimately, all we're really trying to do is get a handle on the same expression here for these upper and lower control limits, and it's all about how are we going to estimate the standard deviation, the spread. That's really what this is all about. How do we do that? And we're going to estimate the sample, or excuse me, estimate the population mean the same way. We'll use the grand mean of our process, and we're going to still use 3 standard deviations, but how do we get there to it? And so now that's where we go back to, in this case, that the expected value of our sample variance was equal to our population variance. That was what, and we use that n-1 version in calculating that sample variance, and that made it an unbiased estimator. Now it turns out that because a square root operator is not a linear operator, that the expected value of S is not sigma, and rather instead it's square root of 1 minus C4 squared. A constant is what that is, and that constant's a function of sample size. So you can imagine as n gets really large, C is going to get close to 0, and then this will actually turn out to be pretty good. But it's not certainly not that case here for where we're at, right? And if we take one more step further, the expected value of S bar is going to be equal to C4 times sigma. So if we want an estimator for our sample standard deviation, the population standard deviation, then we can take S bar and divide it by C4 as our estimator. Right? And so that's what then goes into our upper and lower. Alright, so there's the expected value of S bar is equal to C4 times sigma. And we're going to plug that in over here. And C4 square root of n comes into our upper and lower bound for our X bar based upon S control chart. And you'll see down below then the tabulated values that go along for the upper and lower control limits, as well as those zone values, which I have not plotted on this particular chart. Now, and I'll just give you a brief snapshot. You've got it in your handout, but there they are. They actually do exist. Right, now a couple other things that we need to do before we sort of close out this lesson, and that is that yes, we can also create an S control chart, right? And you'll see the limits and the formulas in the Montgomery and Runger text. Right? I've only presented the X bar charts based upon either R or based upon S. Another aspect here of just the process itself, notice that we do have one that's sitting outside of the bounds, indicating that we have in this particular subgroup something that's out of statistical control, right? Something going on there. Right? As far as the other rules go, it would appear that we really don't have too many others that are real far outside, and we don't have too many all balanced on one side. Well, maybe this is kind of getting a little close to all on one side. So there may be some issues at play and that sort of thing. Now, other big picture things here, and that is that you may have noted, if you just look at the basic numbers here, that there isn't a tremendous difference in the bounds that we created in Xbar versus Xbar. This is 6944 with based upon S, and based upon R, it's 6977. So there's not a lot, especially from a percentage standpoint, not a very large change. And actually, that's something we should expect based upon that the sample size, N, is so small that we wouldn't necessarily see something larger. If we had more sample point or samples collected for an individual subgroup, then we might expect that the Xbar control limits based upon S would actually maybe get tighter than the range, which makes sense, right? Because the sample standard deviation is capturing a lot more about the spread of the data than the range does. The range is only 2 pieces of information out of the entire subgroup sample, right? The max and the min. Now, when you only have 3 data points, well, gee, that represents a lot of the group. But when you have 25, then the max and the min are only 2 data points and may not be all that representative of the actual spread and the body of that particular subgroup data. The other aspect about this is that all I really have done is talked about how do you develop these when you already are fairly confident about what's going on in the process. Now, when I say that you're assuming here that your process is already under control. What do you do if you're just first starting off production and you don't know all that much about what's happening? And one of the things that you do then is that as you move along for the first set of subgroups, then you may just not plot any control limits. You just may go ahead and get the first 20 or so or 25, and then you go and you create the control limits and see what you've got. Then as you move forward in time, then say you collect another 10 subgroups worth of data, you could come back and reevaluate where not only what the grand mean is, but also adjust what the control limits are as well. Right? And you can continue to sort of let that evolve in time, depending according to the processes that are at work, how you set up the rational subgroups, and whether any significant tooling changes have happened along the way. So there's sort of an evolutionary process that one might follow as you're first starting to develop. Now, on the other hand, if you've got a process that's been in operation for many, many, many days, perhaps even many years, and nothing has really changed, you might have a fairly confident feeling for what the population mean and population standard deviation are, and you can relax some of these rules that we've used here, because remember, we're using the R and the range or the standard deviation as a substitution for not knowing the population standard deviation. So if we know that, well then heck, we'll go back and more directly use a normal distribution to look at and work with these results.